It's differential equations. And so I'm going to sell it to you for a little while. Differential equations is going to be vitally important to any of the engineers amongst you. Even if you don't become an engineer, if you become a scientist of any general type, you know, a chemist or a physicist or an environmental scientist or whatever, trust me, you are going to use in your advanced classes differential equations. Basically, you're going to find solutions to these differential equations, and they're going to model something that you're interested in. So it could be the population growth model for halibut, or it could be a model that will tell you the velocity of a moving object under certain circumstances due to gravity, whatever. So these are big things. In fact, it is that big a deal that in Olympic College, we have differential equations 1 and differential equations 2. We have 2 classes devoted to nothing but solving and using and making differential equations. So you can imagine something that takes that chunk of time is pretty big, right? So you're just going to get a little taster of what it's like. You know, it's good to start somewhere, right? But it's got a lot of mileage in front of it. So the first part of today is me getting through what are differential equations, some of the vocabulary, the language that we use, and then we'll get on to doing some work with differential equations. And we'll finish this section tomorrow. And then that's us for this week. And then next week is really our last full week. And during that, we will do the other 3 sections. One of them is really very quick, and the other 2 are going to be like 2 days each. So that's kind of the big picture. And we're done, apart from our test. So let's start off with the obvious. What is a differential equation? Well, we always use DE for short, because nobody wants to write that a lot. So DE means differential equations. And it's simply just an equation, right, that contains a derivative. So here are some examples of differential equations. And there are 2 typical notations. You know, the y dashed means first derivative and the dy by dx notation. Sometimes this notation is more useful, sometimes this notation is more useful. But these are all examples. Do you see that they're equations? They have an equals in it and they've stuff either side. When you solve a differential equation, right, because it's an equation and you solve equations, what you're finding is the function y equals f of x. You're finding out that y is x cubed plus 7, right? You're finding out y is 3e to the 2x, right? That's what you're solving when you solve a differential equation. You're not solving x equals 4, y equals 2 kind of solution. You're solving this is what y equals f of x would be equal to. Now, when you are looking at differential equations, I'm not going into this detail that you need to memorize it, but just for completeness sake. When the derivative only has y dashed in it, or dy by dx, as it does in these 2 examples, it's called a first order differential equation. And when it has a second derivative in it, it's called a second order differential equation. So if you're ever roaming around and looking on the internet for differential equations, and they tell you, oh, this is a first order or a second order or a third, fourth, whatever, that's really all it's telling you, right? The highest derivative that the equation contains is the order of that differential equation. Within differential equations, there are many different kinds, and each kind that's important, at least, is given a name. So you will find in your career, if you do differential equations, that we don't just say it's a first order differential equation. Very often we give it a name. For instance, this is a variable separable. This one here is a non-homogeneous second order. This one here is a first order linear differential equation. This one here is a second order homogeneous differential equation. You do not need to memorize any of those titles, but I just want to give you an idea that differential equations have names attached to them. And why do they have names? Because all first order variable separable differential equations all get solved with one technique. But a second order homogeneous differential equation will get solved by a totally different technique. So if you can look at something and tell what kind of differential equation it is, right, you can give it the right name. By doing that, you've also decided how you're going to solve it. And that's important that you know what method, because the methods do not share a lot of commonality. They're quite different looking in every situation. Now, when you solve a differential equation, it can either be called a general or a particular solution. For example, see this differential equation here? It has a general solution, 2x to the 4 plus x squared plus c. If your solution contains a constant, right, a plus c, but it might not just be plus c, sometimes it's cx, right, or cx plus d. If it has letters in it, right, that represent unknown constants, that's a general solution to the differential equation. When you know everything, right, there's numbers everywhere. That's called a particular solution. And for instance, can you see that this general solution is just this particular solution with the c replaced with a 7? If I replaced the c with a 22, that would be a different particular solution. Okay. Now this fellow over here, that's me just getting into the some of the other jargon that we use. So typically when you solve a differential equation, you find its general solution first. So you find this one, and that might be all you're asked to do. But occasionally, quite a lot of the time, you then solve using some extra piece of information. So you'll be told in the differential equation something extra, like the value of the function at 0 is 10, or the first derivative at 1 is 90. And this extra piece of information will allow you to generate a particular solution. So in this case here, it would allow you to figure out that that was 7. And this extra information, right, for instance, that guy, this extra information is very often called the initial or boundary conditions. So if you're looking at the future and you're looking back at differential equations and you're told some extra information, and it would be called the initial or boundary condition. Are we good with that vague big picture of what differential equations are? Some of the namings, some of the things that we're going to do. So far, so good. Okay. So what we're going to do today, for the rest of today, is we are not going to solve them. We are going to check, is this particular guy a solution? So we're just basically saying somebody else got the solution. We're just checking to make sure it's right, that it works. And that's a good skill to have, because in differential equations, there's a lot of work involved and a lot of places you could go wrong. So wouldn't it be nice if you could check your answer to make sure that you did it right? So checking is a pretty important step in the process. So here is first example. We are being asked to verify that this function is a solution to the differential equation. Oops, sorry. Scanned badly. To that differential equation here.
That's an equal sign with a slash through it?
No, it's me making a mistake. That's what I should have written, right? Y dash plus 7y equals 7e to the x. And we're being asked to prove that this fella up here actually is a solution to that differential equation. Okay, for most of you, if not all of you, this is the first time you've ever seen a differential equation. How do you think I could check that this actually works for that equation?
Take the derivative and then plug in the values.
Yeah, pretty much. Substitution is how we do it. So I'm going to take the original function. I'm going to find its derivative. Now, if you differentiate this guy, I believe you get -7 e to -7x. Are we all comfortable with that? Now, according to this differential equation, the first derivative plus 7 times y, which I'm going to call the left-hand side, and I'm going to find out what that's equal to. And if it ends up equaling 7e to the x, then that's it, right? It works. So if this side equals that, we've proved it. Right. So you take this fella, who's 7/8 e to the x, take away 7e to the -7x, and you add 7 lots of this guy. Oops, where is it? 7 lots of this guy. So if you want to if you want to check a differential equation, take the left-hand side and prove that it's equal to the right-hand side. Let's see what this looks like. You've got this guy, take away that guy. 7 times this is 49/8. 7 times this gets you that guy. Well, that guy cancels out with this fella. If you add this guy to this guy, you get 56/8 e to the x. But wait a minute, isn't that just 7? And good news. Check. It works. So the left-hand side equals 7e to the x, the right-hand side. Any questions about that, or do we feel comfortable about that? Okay, this is version 2. We have to prove, or check, I guess is a better word. Check that this function is a solution to this differential equation. So what I'm going to do is I'm going to take my left-hand side and I'm going to figure out what it is, and I'm going to take my right-hand side. I'm going to figure out what it is. And if the two sides, actually, if this side equals that side, we're good to go. So let's start with the left-hand side. Right, the derivative of this fella here. How am I going to find the derivative of -4t cosine t?
Product rule.
Great. So it's going to be f dash g plus f of g dashed. I think I've got room. T. Differentiate this guy, you get -4. Leave this second guy alone. Leave the first guy alone. And derivative of cosine is negative sine. Take away 4. So this becomes negative 4t cosine t plus 4t squared sine t. Take away 4t. And that's the left-hand side. I'll put a box around that to try and remember it. Now, the right-hand side has to be dealt with as well. And some's not right. Oh, the right-hand side is this fella. And y is all that, so it's negative 4t cosine t, take away 4t, plus this piece. Now, is this fella him? Well, a little bit of shuffling, would you agree they are the same? So that's, we've shown that it is a solution. Sam?
You walk through that last bit again. I'm
Yeah.
struggling to keep up.
Okay. We have left-hand side equals right-hand side. The left-hand side we've just completed. Right? We found the derivative and multiplied it by t. And the right-hand side is this. So it's y. The y gets replaced by what it's equal to. So the y became these two. And then we have a plus that guy. So this is what the right-hand side looks like. It's y plus 4t squared sine t. Now, I know the left-hand side is this fella. I know the right-hand side is this fella. Would you agree that they are equal? They are the same thing. That's how you prove that you have, in fact, got a solution that works. Whatever the left-hand side equals, it should be the same answer as the right-hand side. And we work it all the way through to, in terms of x or t in this case, right? You don't leave any y's left over. You don't leave any derivatives left over. You convert everything into whatever the variable happens to be. Better? Right. Now, there are some more examples of that. They're just phrased in a slightly different way. And I'm going to show you some homework questions so we can see what they're like. It takes too long to write them down. The ones I'm interested in are down here. (10) and 11. Now, it's asking you which of the following is a solution of this differential equation, which is this guy here, right? Now, the awkward thing about it, or maybe not awkward, but the interesting thing about it is that there might be two answers, or there might only be one. So we have to check each one in turn to figure out which one is a solution. So here's the differential equation, and it might be that one, it might be this one, it might be the first two, it might be every single one of them. I think the only thing for sure is it's probably at least one of them, right? So here you're not actually given one question and being asked to check, is it a solution? You'll be given 5 possible solutions, and your job is to find out which ones work, which basically means you do the same thing 5 times.
I
Kathy?
think it only lets you click on one, though.
Is it? So only one of them's correct?
Mhm.
Okay, so when you find the right one, stop looking. Right, when you find the one that works, then you stop looking. Oh, that's pretty, because you could easily get a solution that has two. Is there another one up here that might have more than one? Yes, here they are. Question 4 is the same question. Ah, there we go. In question 4, you may have 2 correct answers. You may have 4, which means you have to look through all of them. In questions 10 and 11, since only one of them works, once we find the one that works, we know we've got the answer and we don't need to do anymore. So let's do question 10. There are 5 choices there. It truly is a guess. Which one of those 5 do you think we should check? And if we're lucky, it's the right answer. And if it's not, well, we still have done something useful, right? We could then, if we had time, we'd do another one until we got it. So which one of the 5 you want to guess at 10? 1, 2, 3, 4, or 5?
3.
3 gets the job. Okay, so 3 is y equals 4 cosine x. Take away 3 times the sine of x, cosine of x, okay?
Are
And
we supposed to be able to see your paper?
not yet, but you will in a second. Y dashed plus the tan of x times y should equal 3 cos squared x's. Okay, let's stop sharing. And I was basically just getting the question set up, so there we go. Put that out of the way. So I want to figure this fella out. I'm going to start with the y. 4 cosine x, take away 3 sine x, cosine x. And I'm going to find its derivative. Well, if you differentiate 4 cosines, you get negative 4 sines. Would you agree that this is an f and this is a g? So I'm going to have to do the product rule. So negative 4 sine of x's. I'm calling that negative 3. Is that negative 3? Yeah, that's negative 3 sine x. I'm going to call that f. So when you differentiate negative 3 sine x, you get negative 3 cosine x. And then you leave the other one alone. And then you add the untouched first one times the derivative of a cosine, which is negative sine x. So that looks like negative 4 sine x. That guy is negative 3 cos squared x. And this fill here is plus 3 sine squared x. So that's what y dashed is equal to. So I'm going to take y dashed plus this and hopefully prove it's that fella. So y dashed plus the tan of x times y. Negative 4 sine x, negative 3 cos squared x. Bit worried about that. Plus 3 sine squared x. Plus a tangent, which I'm going to write as sine x over cosine x. This fella. So I have negative 4 sines, negative 3 coses squared, plus 3 sine x squared. If you multiply this by the cosines cancel out, and you're left with 4 sine x If you multiply this and this together, the cosines cancel out, and you're left with negative 3 sine squared x. And let's see what we get here. That gets killed off with that. This gets killed off with that. And the answer is negative 3 cos squared x. Unfortunately, that's not a solution. It's darn close, isn't it? It was almost a match. But not the solution. I'm not going to do any more of them, but can you imagine you just tried the next one and then the third one and then the fourth one, and eventually you get one of them that would work. Are we cool with the process of how you would go about it, even if we didn't get the solution that we were hoping? Right? Do you know it's called Murphy's Law? This is one of the flavors of Murphy's Law. Do you know if you start at the top and work your way down, it's always the last one? If you start at the bottom and work your way up, it's always the first one. If you randomly do it, it's still the last one. That's called Murphy's Law, right? The number of times that has happened to me in the past when I was a student was almost laughable. You could almost bet that it was going to be the last or the second last every time. I was never lucky at the pick the right answer question. Just not my thing.
Sounds like a 50-50-90 rule, where when there's a 50-50 chance, there's a 90% chance that the engineer will pick wrong.
You're right. It does sound exactly like that. Yeah. But hey, at least we did the process, right? I was hoping I'd get a one that worked, because it would have been kind of nice, right? That we got the right one. But there are 5 chances, so that was pretty slim. So I'm now moving on to a slightly different question. And this is a version of question 3. And it's not asking us to check is the solution directly. It's saying to you this, so I'll write it down. What value, or values, it could be more than one, of k does this fella is a solution to this second order differential equation? Not that you need to know that, but that particular one is a second order homogeneous differential equation. She's just interested in its name. So I'm not just going to check that that works. I'm going to also find the only values of k where it does work. So it might work for cosine of 2t, but it might not work for the cosine of 10t, right? There's only specific values of k where it's working. So I'll start off with my basic building block, which is that fella. Since I'm going to be using the second derivative, right, I need to find the first derivative before I can get the second. So that's what's happening here. If you differentiate the cosine of kt, you will get negative the sine of kt. What else do you get? Times something else.
Times k.
Right. So are you all happy about where that k here came from? It's basically a chain rule. Now, if you do the second derivative, which means you differentiate this, if you differentiate negative k sine, you'll get negative k cosine of kt times another k. So now I'm going to take my differential equation, 25 second derivatives needs to equal negative 9y. And 25 of these guys gets me 25 of this fella. is going to equal -9 of this fella. And there should be, yeah, that should be it. Now, that's -25 k squared cosine kt is -9 cosine kt. Right, and we need to solve for k. So, as long as you do it to both sides, it's okay, rule. So give me some I can do to both sides.
Divide by cosine kt.
And provided the cosine of kt is not 0, that is allowed. And we'll assume it's not. Where are we off to now?
Does that divide both sides by -25?
Yep, which means you get positive 9/25. Where are we off to now?
Square root.
And would you agree that there's a plus and a minus square root?
Yes.
Which means that there are two answers, positive 3/5 and -3/5. And in the homework, there's a box and you put a comma between them and it needs a comma or else it'll tell you you're wrong because it's awkward, right? But we follow the instructions and we put a comma in there. So only if that is 3/5 t or -3/5 t will this fella be a solution to that differential equation.
I can't quite see the very bottom. Can you move your paper up?
Is that better? Right, let me see if I can, how does I do that? Does that help?
Yes. No.
Too much?
Now it's very too far to the right. Perfect.
How's it? Perfect. Can you still read the top line? Because I don't want to move it too far up and then you can't read the other part.
Yeah.
Top line good?
Yes.
Right, we are good. Okay, now I'm going to put that engineer rule and Murphy's rule to the test. So for essentially the last question for today, I'm going to put on the screen, I think I'll make it a bit bigger because some of you don't have a large screen probably. There is 5 guys, one of which is the solution to that differential equation. You've only got 3 minutes to find them.
We can't see it.
Then that would definitely be Murphy's Law. Now you've got 3 minutes to see them. Go for it. And hopefully one of you will randomly pick the right guy to do it with, because you've only got time to do one. Okay, last few seconds. Let's kick over. Did anybody get the one that worked?
I just did. I did
What
4.
number?
It was number 2.
So one didn't work, so you did 2?
I did 4.
Oh, 4 didn't work, so then you did 2. Right, do we
Yeah,
get agreement?
same.
Is it the second one is the one that made it? So you might have unfortunately picked one of the others, which is pretty much what I would have done. So let's verify that. And I don't think have I done attendance yet? Okay, why don't you do attendance while I get myself set up here? Okay, there's 3 people missing, or 3 people who haven't said hi. Make sure you say hi. Okay, here we go. I believe that's the second one. In this equation, really only use the first derivative, so that's what I'm doing. I'm going to leave it in this format.
That's not
Multiply
the
by
second
the
answer.
power, reduce the power.
That's not the second one.
That's not the second one.
No?
No.
What the heck is that? Who knows?
Someone said it in chat.
So 4x minus 2 to the negative 1. Or
4x,
2x to the negative 1.
2x
Minus
to negative
2x to the negative 1, yes.
1. Okay. I think that's probably my scanning that did that. I went and come back and saw the wrong one. Okay, so derivative of that is 4. Multiply by the power and reduce it by 1 is that. Looking good? So we're going to take x, y dashed, and add a y. And if all of that ends up being 8x, we are good to go. Now, x times 4 is 4x. X times this guy just reduces that power to negative 1. 4x, oh, that is cool, isn't it? Kill, add me. We got it.